Morning, everybody. How are you out there? Hope everybody's doing well. Just wanted to put out a quick reminder at the beginning of the video here that today is the last day of school before we go on spring break. So I hope everybody's excited for spring break. Maybe not excited is not the right word, but at the very least there'll be less assignments, I guess. Um, I will be around for spring break. I'm obviously not going anywhere. So if you would like to get a hold of me, you can send me an email or drop me a message in our Google Classroom. Either of those options would work for me, and I will try to respond. So just so you know that I'm still here and around. If there's anything I can do for you. I don't know if I'll get in there and do any more streams or anything through spring break. School's canceled for the week. It's supposed to be a no nice easy time for us. We're not supposed to, or we're supposed to maybe something to lower the amount of stress. I'm sure that everybody's having has enough things to worry about. So we will, at the very least, have a little break from new content, at least new videos and things. So keep your eye on the classroom if you want. If you don't want to, it's you're right. You're on holidays, so enjoy those. Try to find something to enjoy for those weeks. Meanwhile, we're going to finish up ecology today, and the other thing we're going to finish up is our chemistry unit. The chemistry unit has a sort of test, final assessment has been posted in the classroom. So if you can do that, that would be great. It's pretty straightforward, mostly multiple choice kind of things because those work really well online. And I will look at those and your other work and put those all together into a midterm mark that's going to be posted on your what do you call them, report cards. Yeah, those report cards will go out after we get back from spring break. I don't remember exactly the schedule, but we'll get to that. It's a really weird time. Don't worry about it too much. It's nothing to stress about. We're doing what we can to figure that part out. All right. Well, let's get into it. We just finished on this ecological footprint idea. So the idea that different foods have different outputs for us. In this case, I just noticed at the bottom here that this is a British, this is based on production in Britain. So the ecological footprints could be a little different in North America depending on how we do the farming and how we do the, I guess, husbandry in this case of raising the animals. So that's something to consider as well. If you want to look at the amount of energy requirements for a pound of meats or a pound of different foods, you can see that the amount of energy you need to put in to get a sample of, to get 1 pound of beef is quite a bit. So this is shown in kilowatt hours per pound, which is an interesting measurement for food. But it is interesting, how much energy do you have to put in for 1 pound? Now I'm not sure 1 pound of apples versus 1 pound of pork. The energy density is probably different there as well, so you might get a different amount of calories. But considering how little energy goes into making corn, for example, or milk, it's likely that the balance is going to be there. All right. If you haven't checked your school email recently, there was an email that went out just recently. Went out this morning, and it has a bunch of links for. I just got the email right now. It has a bunch of health links for ideas for things for supports for you. And there's also on the the Winnipeg Adult Ed's Student Services website, there are some additional documents there if you're in need of some assistance for anything, so psychological supports, assistance in buying food, including from Manitoba Harvest, and a bunch of other instructions. Those are all available in your email right now, or if you go to our blogs on the WEC website, you can find some links to some of those services from the Student Services blog. Okay, those are our announcements for the day. Um, okay, so we're gonna get into the cycles now. So this is one of the main sections of this booklet. In fact, there's probably only 3 sections. There is the trophic levels, the energy pyramid section. There's a section about matter conservation, and then the final section, which I am blanking on right now, but we'll get to it eventually. I just looked at it a second ago too. Oh, bioaccumulation. Okay, so conservation of matter and ecological cycles. So matter cannot be created or destroyed. Therefore, all biotic matter, all living matter, must originate from the environment. Um, and that means that all of our biotic matter actually originates from abiotic matter, from unliving. So all of our living matter, right, this is our living matter, living, comes from originally not living or non-living. So this is what Neil deGrasse Tyson is saying when he says we're all made of star stuff. Um, at the beginning of the universe, there was just a big bang. It was just a bunch of rocks and stuff all shot out into space, and and then after that big bang, those rocks and things like collide together. They form planets. They form all these other features, and then those planets eventually combine those elements. Excuse me. To form some of the living elements. So photosynthesis allows for abiotic gas, for not living gases like CO2, O2, water, to become part of the plant cells, while also incorporating other elements like nitrogen directly from the soil. Nitrogen, magnesium, and a couple other elements, sulfur. Consumers incorporate these elements into their body as they consume the plants or other consumers, allowing themselves to grow and reproduce. This implies that not only is energy in flow, but also matter. So we had a cycle of energy. The sun gives energy to the plants give energy to the animals that eat it, the animals that eat it give energy to the other animals that eat them, etc. Now we're also talking about the flow of matter. And what does that look like? So the first piece of matter that's going to move is the carbon cycle. So this is the movement of carbon through our environment. And the first step of that carbon cycle is photosynthesis. So plants contain an element, contain a molecule. This is chlorophyll. It is a light sensitive chemical. So it's a chemical that is light sensitive. Let's see, maybe we can pull up an example of that. Let's go chloro. Keyboard doesn't want to work. So it's a pretty complicated chemical, but let's see if we can find the chemical here. Here we can put this little picture. So this is a good image here. So we have the plant leaf. Inside the plant leaf, there are these things called chloroplasts. Inside the chloroplast, we have chlorophyll, which is this chemical. It's actually really interesting. It has this sort of metal on the inside. Notice that there's a little bit of magnesium here. There's some nitrogen. At all of these little spots here, all of the corners, these are carbon atoms. So it's a pretty complicated little network of carbons. Little, it's actually kind of big. And there's probably a bunch of hydrogens as well. So those are all carbons, and including all these C's on the outside. So those are all carbons. Boy, it's gonna get real messy. Then there's a whole bunch of oxygens over here. Not too many. Notice this one that just says C20. That means it's just like a big long chain of carbons there. Um, so it's a big messy molecule there. But made out of the same stuff you already know. So you already know something about carbon and nitrogen and oxygen and magnesium. You know where those are on your periodic table. It's the same elements that make up you and me. And so this chlorophyll chemical is able to absorb light, and it undergoes a bunch of different chemical reactions with this light and essentially allows the light to be converted into a unit that the cell can use, that it can use to convert carbon dioxide and water into oxygen and sugar. Whew, tired, man. I don't know. More tired at home than I am when I'm at work. I think at least at work I can stand up and move around. The sugars are then used to nourish the plant itself. So the plant does use the sugars to burn up as an energy source. And it's also used to build up structures in the plant. So, for example, cellulose is made from sugars. Starches are made of sugar. And so these can also be stored in as energy, so in starch. So this is why something like a potato, right? A potato, even though it's not sweet to eat, can be high in calories. And that's because it's high in starch. So potatoes, they're not sweet, but high in energy because the sugar is stored as starch. Now, if you wanted to eat a potato, you can't just bite into it. Yes, making me yawn also. Sorry about that, Carla. I don't know what's happening here. I've been up for already an hour or so, I guess ecology is not the most thrilling subject in the world for me. I'm more excited about chemistry, right? Should be excited about this section. This is the chemistry section. Okay. So, so this carbon stored in the sugars. I think we've talked about this before. So now we're going to talk about cellular respiration. So the cell uses the sugar up to power to power its to power function. So this is called a respiration. All living things convert food into biochemical energy. We think of respiration as breathing, but that is just how our oxygen gets into the body. So especially if you go into a grade 11 course, you'll talk about the different ways that we can talk about respiration. There is respiration where that we think of like for our bodies, which is sort of bulk body respiration, where we bring oxygen into our body, but that oxygen actually has to end up in the cells. Yes, being for sure. Uh, so the oxygen has to actually get into our cells before real respiration hits us. So the actual respiration act is when oxygen reacts in essentially what we would call a combustion reaction. Just it's not forming fire like we think of when we think of combustion. It's just breaking down the carbon into CO2 and water. So another reason why we teach the combustion reaction in our chemistry unit. It uses oxygen to burn sugars. So let's be more specific. In a combustion reaction, Most living things, they use this same oxygen in the same way. So that's why we on it might be. It's definitely one behavior that maybe if you're feeling tired, you might need to take a big yawn to get your body some extra oxygen. I That does kind of sound that sounds kind of right. I wonder if that's the case. I also had heard that it's a learned behavior. Do we yawn to get more oxygen? One is that we report tired. Okay. Yeah. Yeah, you're right. You're right, Carla. Or at least one theory is we yawn to compensate for slower breathing. So apparently, Carla's on the right track here, making that connection right to what we're talking about right now. Uh, we Sometimes we need to yawn to bring in extra oxygen, especially if our breathing has slowed down, or maybe you're tired and you're slowly breathing. It could be even the case that when I'm speaking, I'm talking a lot and a lot, a lot, and then I'm not really breathing in very much. So my body starts to run out of oxygen, and then I have to take sort of a big. My body says, "Hey, get a yawn in there because you need more oxygen. You're running low." So maybe I'll take some more breaks to breathe. I definitely tend to just start talking and not stop. Okay. Whew. A couple good deep breaths that might actually make me work better anyways. There are a few organisms that don't require oxygen. They can use different ways of breathing. So, for example, there are these are called anaerobic without oxygen. So this is called anaerobic organisms. Most living things that use oxygen, these are called aerobic organisms. So yeah, yeah, it is socially contagious. That's for sure. Those yawns. Um, so aerobic organisms. You might notice the word aerobic if you do aerobics. One of the concepts behind exercises that are aerobic is that they are done at a pace that allows you to breathe. So aerobic exercises, aerobics, you're supposed to be doing those in such a way that you're always breathing in. In anaerobic exercises like weightlifting or some of the other types of or those HIIT programs like high interval training, some of those are considered anaerobic, and they hit a different type of muscle group. They have a different type of muscle development, and the concept is to starve your muscles of energy, or starve your muscles of oxygen to get them to do something else, to get them to burn energy in a different way. So aerobic and anaerobic organisms are also are there are both types. Um, Yeast is probably the most common anaerobic organism that we interact with, because those anaerobic yeasts, they can take sugar. They still use sugar, but they don't use oxygen to break it down. They use water, and the water and sugar are mixed together, and then they form alcohols. And so when you're producing wines, you can when you're producing wine or beer or whatever, or any spirit, you usually use a yeast, and that yeast takes the sugars in and converts those into alcohol. That gives your drink its alcohol content. You also have other yeast that will turn the sugar into carbon dioxide, I believe, and that's the one that you would use in bread. I believe bread yeast. Bread yeast. What would that be? Respiration. The yeast in your bread uses the process of cellular respiration, where the glucose is converted to ATP and carbon dioxide. Yeah. So yeast makes carbon dioxide, and then wine yeast. It turns into alcohol and carbon dioxide. So I'm not sure if do you get alcohol made in your bread as well, I wonder. It would be burned up right away by the. Hmm, don't imagine them being that different. No, it is alcohol and carbon dioxide. So it is still alcohol and carbon dioxide. So these organisms, yeast, so this breaks down uh, sugar into alcohol and carbon dioxide. So that's really interesting. I wonder what that's what does a leavened bread taste like? Does it taste kind of alcoholic? I don't eat my dough before I bake it. Certainly, the alcohol once it goes into the oven will probably be burned up. This is also why you can make I just read a recipe for a beer bread where you take a can of beer and mix it in with your flour and stuff, and then that will make a fairly the carbon dioxide is already there, and it's a very fast bread you can make, and you're sort of simulating this yeast action. Okay. So your muscles will also, in anaerobic exercises, your muscles will actually take lactic acid, which will start to make lactic acid instead of making pure CO2. And so this is a half action that they can do for breaking down sugars for energy when they run out of oxygen, or they run low on oxygen. When animals and plants use oxygen, the chemistry is similar to combustion. So here's burning a natural gas like methane. So this is methane being burned, and we see that same chemical reaction we've always used. And then if we go and burn sugar, we see that the products are the same. So same products, water and carbon dioxide. I lost my chat. Okay. So the carbon cycle is the idea that this carbon that we get from our plants has to go somewhere, and it will go and it'll cycle through an environment by the process that plants use carbon dioxide to make sugar. We get our sugars and oxygen from those plants. We then breathe out carbon dioxide after we decompose the sugars in our body, and those plants will use the carbon dioxide again to make more sugar, making a cycle. So plants use the CO2 and water to make sugar and oxygen. Living things use oxygen and sugar to live and make CO2 in the process. But this, of course, gets a little bit more complicated because some critters also eat other critters as well as plants. So then the cycle gets another layer to it. And then not every tissue gets eaten, so there's carbon that's also turned into dead matter. Those dead matter has to be decomposed to be brought back into the soil so that the plants could use it again. Because soil gets compacted into the earth or gets eroded into the sea, this gets even more complicated. And then we also have seaweed and fish and all that sort of stuff in the ocean. And so the carbon and the oxygen are cycled in the sea as well. And then there's also carbon that's released by fires and volcanoes and uh, combustion industry. We gotta put cars in here, right? Machinery, all that sort of stuff, like cars, etc., combustion engines. So here's a very simple animal-focused example. So this is a carbon cycle that you can play around with or think about. So let's just follow it from the sun first. So here the sun helps the plants produce CO2 at the beginning. Or the sun helps the plants convert CO2 into sugar. Now those plants also use that sugar for energy. So actually plants do produce a little bit of CO2. They of course consume more CO2 than they produce, but they do produce a little bit of CO2 through their own cellular respiration. So this is cellular respiration of plants. Oops. We have carbon compounds in the that are these carbon compounds down here. Those are things like your leaves, your sugars, your starches, etc. So I'm gonna just use a different color here. Uh, so carbon compounds, we're talking about leaves, stems, fruit, roots, etc. Those carbon compounds, especially things like fruit, or in this case acorns, they can be consumed by the primary consumer. So this one would be our primary consumer. So I'm going to use a 1, 0 primary consumer. Those primary consumers are going to exchange carbon with the secondary consumer. And then the tertiary consumer, the top of the food chain here, tertiary consumer, the wolf, they also get carbon from their prey. They don't eat a lot of trees. They don't need to. They are eating things that have eaten from the tree. From that point, they will produce CO2 through respiration. So this is just breathing and living, right? So CO2 goes back in the environment through respiration. Respiration. So this is, CO2 from living. And then when those organisms die, their bodies become part of the soil and eventually become decomposed. And so death and decomposition, some of their carbon compounds go into the ground. So this might be, forming fossils, or um, or other organic rock. So there's a couple other options down there. There's one where the organism is pressed between two layers of rock, and they're pressed so hard they turn back into a pure carbon, and they leave sort of like blackened imprint. Now, this doesn't matter what organism it is, so both of these, excuse me, are forming rocks. We, of course, have our decomposers down here. Those are our bugs and our worms and our bacteria, and those are going to help in that death and decomposition. And so through that death and decomposition, they're going to slowly reproduce the CO2 until the CO2 actually leaves the air through the respiration. This is respiration of the decomposers. And so that's sort of how carbon can cycle. We have two more cycles to do. We have the nitrogen cycle, which we'll do next. There's the acid rain again. Um, and we'll talk a little bit more about acid rain this time. But there's the nitrogen cycle that we have to go through. And I feel like there's one more. Maybe it's the bioaccumulation right after that. And then bioaccumulation. Okay, so I'm not sure if we should take a break at this point. That's probably not the worst spot to end for before spring break. You do have the test that's been posted. It feels like, I don't want to waste your time by taking only a half class. Would you like to keep going for the nitrogen cycle? It's a pretty similar process, and then I can leave you to work on your test. I think I've already convinced myself. We're gonna do the nitrogen cycle. So we're gonna skip forward to the nitrogen cycle. Nitrogen cycle takes place on page 21. So we're going to skip forward to page 21. There's a section there about acid rain, which we did cover in our chemistry unit. Maybe I'll do a quick video about it later, or we'll come back to it when we come back from the break. But let's get through this nitrogen cycle, and then we'll feel like we definitely covered a good majority of this ecology booklet by the time we come back. I do have my student teacher, Matthew, who you've all met. He'll be starting to post videos soon about physics. So he's working on his physics videos right now and his physics materials, and he'll be posting those through the classroom. And we'll probably get him started right away when we come back from the break. I'm not sure if we'll just take a break from chemistry, from the ecology until that time, or what. Haven't quite figured it out. Maybe a week of ecology is enough. Um, uh, yeah, we'll figure it out. But I hate to leave a book half empty. That's the other thing. It'll probably only take us another 2 days or 3 days when we come back to finish up the last lessons in this booklet. It is a very short booklet, and then we'll start up on the physics unit. And yeah, there's not really any clear direction yet as to whether we'll be back in school when we come back. We're gonna be taking our initiatives from the province, and it's actually almost time to check in with the province. They give a daily update at 11 o'clock, so if you are on top of things, or if you're interested in that, you can look to the updates that are usually around that time. Oh, we just got notice that this morning the province has launched a program to help cope with COVID anxiety. That's really nice of them. I like that. It's a $4.5 million initiative for an online therapy program. Very cool. So that might be something that you might be interested in. Okay, let's get back to nitrogen. So nitrogen cycle, so nitrogen gas makes up about 79% of the environment. It is an essential part of our organisms. There's everything from your proteins to your DNA require nitrogen, but most of the nitrogen is trapped in the form of air. This nitrogen gas is very unreactive, very stable. It's actually very difficult to work with nitrogen to get it to do anything useful. In my own lab experience, we used to use nitrogen as a benign gas. If we were worried about chemical reactions, we would use nitrogen gas to stabilize the chemical reaction, and we would pump nitrogen gas into a chamber and pump out all the oxygen. So that was sort of how we worked with nitrogen. It was it's we I consider it almost like a noble gas. You can't really do chemistry with it. So it's very stable and reactively non and relatively non-reactive. So it's hard to capture. So by capture I mean hard to change its form. So the nitrogen must be in the form of a nitrate to be useful by other organisms. This process of converting a nitrogen gas into a nitrate is what we call nitrogen fixing. Fixing as in like to affix something, to stick something on. Um, oh my stream is looking not great. Oof, got a lot of dropped frames here. All right, hope that's not retaining enough data. Okay, we are back. Hopefully that wasn't too much of a bump for you. Um, um, okay, I think I'm back. Okay, sorry about that. It looks like I had some streaming issues. I had some processes on the background that looked like they were eating up some resources there, some network resources. Okay, so nitrogen cycle is very complicated. So we're going to talk about sort of a condensed, the Reader's Digest version of the nitrogen cycle, and we're going to go for the sort of quickest version of this cycle that we can manage here. So there is one process which is nitrogen fixing by lightning. So the energy of the lightning, I would rather these be inserted here. The energy of the lightning interacts with the oxygen and nitrogen, and that will make nitrates. Again, I'm getting a buffering problem. I'm just going to do a check, make sure the kids aren't streaming. Are the kids on Netflix? Okay. Don't know what's going on with my YouTube. It's not getting great stream here. Nitrates are the nitrates can then be dissolved in the water and then are absorbed by plant roots. And So the nitrates, they get dissolved in water and then they get absorbed by the roots, and then the plant can convert those absorbed nitrates and turn them into DNA and turn them into proteins, turn them into the stuff that the plants need. So really essential process. Animals then go and eat those plants, and then they convert that nitrogen into their own bodies by digesting the plants and converting them down into into their converting them into parts of their own bodies. Now the more common way that we get nitrogen. The more common way to get nitrogen is to get it by nitrogen fixing. And so in nitrogen fixing, we have nitrogen fixing by bacteria. We have bacteria that are these specialized bacteria, and they will absorb nitrogen from the environment and convert them. There's a especially common type of bacteria that lives on the roots of legumes. So these are your peas, your beans, your clovers, your alfalfas, and these plants will make these plants, the legumes, they make sugar that feeds the bacteria, and then that bacteria provides nitrates for the plant. And so this is a really essential process. There was the traditional way of raising corn or maize by the indigenous people of South America was actually what was known as the Three Sisters technique. And the Three Sisters technique would take a bean plant, a maize plant, a corn plant, and I believe it was a yam, and the three plants would be grown together in the same field. Growing them together, the beans would provide nitrogen for the corn, and the corn would provide food for the people who were interested in eating it, and then the yam or the squash or the gourd or whatever they're growing, would have very prickly vines, and those prickly vines would keep out some of the predators like a would keep out some of the predators. So I am not super pleased here. I don't know what's going on. My health is jumping up and down all over my stream. So this was called mixed planting. I'm just gonna look up the Three Sisters here. Planting. Let's see if I can get a picture. There's a diagram. Here's the. It was squash. That's what it was. So this was the Three Sisters. Oh, great. My data's died completely. Awesome. What is going on with my network? All right. Well, it looks like my stream has gone down. So I'm going to have to end today. I don't know what's happened. Looks like my stream quality has dropped. All right, I think I'm gonna have to end for today. It looks like I can't get a smooth enough stream going, so I'm going to just end right now, and I'm gonna try resetting some things. Please continue to work on the test that's been posted online. I will post another, yeah, uh, I will end now and post a video later. Sorry about that. To do the final assessment for chemistry. Okay, end this stream. Not sure what's going on. I'm gonna end this. See you later. Have a great spring break. We'll talk to you later.